Good morning, guys. Today I'm having cookies for breakfast. Now, as much as I'd like to just chomp down on these, I've got a few things to tell you. I want to use these cookies to help you understand plate tectonics and how tectonic plates move around together. If we were doing a model of the whole planet today, we would have the outer layer, and then down in the middle we would have the core. We'd have the inner and the outer core. We're not worried about the core today. We'll get rid of that. Right now we're worried about just the crust, and the crust honestly is just really a thin layer on the top of this. If you had all the mountains of the earth put onto this and the texture was just right, and you ran your fingers over it, you might be able to tell a bump where you have the highest mountains, but for the most part, your fingers would feel like this is just a smooth ball. Looking at a cookie, we're going to have 3 layers that we talk about. We're going to have the top layer, which is the crust of our Earth. The next layer down is going to be the lithosphere, which is the moving portion of the crust of our Earth. And then down below that, the last layer down here is the asthenosphere, which is the molten plastic squishy layer, the layer that actually does a lot of the moving around. We're going to try and demonstrate this, show some of the plate movements using cookies. First, we're going to do a divergent plate boundary. So we've got our cookie, and the forces of the earth are pushing the plates from one side to another, so they're moving out. We take the cookie, top of the cookie, break it, and it starts to spread apart like that. This is a divergent plate boundary. And this is what's happening in the middle of the Atlantic Ocean. The mid-Atlantic ridge is a divergent plate boundary. Divergent means moving apart. Next, we're going to do a transform boundary. Now, a transform boundary is what we have in California. California has San Andreas Fault, and we have parts of the plates that are moving one direction and parts that are moving the other direction. They're still on a flat level, but they are moving and shifting, and you have a shift like that. This is a transform boundary. The California's transform boundary has one plate moving this way and another plate of the crust moving this way. And then we end up with a big fault line along California called the San Andreas Fault. Now this last one's really fun. This is a convergent boundary. This is where 2 plates are pushing against each other. What do you think is going to happen? Types of convergent plate boundaries. You can have a continental plate merging with a continental plate. You could have a continental plate merging with an oceanic plate, and you could have an oceanic plate merging with an oceanic plate. And those are 3 types of convergent plate boundaries. So with a convergent plate boundary, you have 2 plates running against each other. In this case, we have continental and continental that are pushing against each other, and you end up with a mountain uplift, a rise in the mountain, something like this. This is going to be a continental convergent plate boundary. Now the big difference between a continental plate and an oceanic plate is its density. Not only are continental plates bigger volume-wise, they take up more space, but they also have less substance to them. So to simulate that, I'm going to scrape some of the stuffing off of one side and put it on the other side. So we've got a double stuff plate boundary. So this is going to be the thickness of my continental plate. This is going to be the thickness of my oceanic plate. And we have 2 plates colliding against each other, and as they collide, the oceanic plate dips down underneath the continental plate. So we're going to turn this angle here to downward. So the continental plate is coming this way, and the oceanic plate is going to slide underneath because it just can't compete. It just can't compete with the amount of continental plate. And the last one is going to be oceanic and oceanic plates. In this case, you're going to still have the same situation where from the top view, the plates are pushing against each other. From the side view, you're going to have something similar to the continental plate and the oceanic plate, where one of them just is a little more dense than the other, it has a little more substance, and it goes beneath it. So we'll turn this side view, oceanic plate, one of them wins, one of them subducts, goes down deeper into the earth. So we're going to look at this water here is the mantle, the molten interior of the earth many miles down. And this big thick piece of styrofoam is continental crust. It's big, it's thick. Then we have oceanic crust. Oceanic crust is always much thinner. So whenever there's a collision between continental and oceanic crust, the oceanic crust subducts. Now sometimes that results in the continental crust pushing upward and creating a rise. If oceanic and oceanic crusts collide, then you have subduction of one of them. One of them goes under the other.